and apply MPC to grid-connected converters. Am I right, Arya? Yes? You will be able to do these things, yeah? I will check. So, now, what is the advantage of MPC? So, if we see that PI controller or MPC, I can say that first, MPC is much more better because it is faster. So let's see what other advantages are available from the MPC. MPC is very logical concept, predicting system behavior over a time horizon and optimizing control inputs accordingly. It's very straightforward. So you have the behavior of the system, and based on that, optimize it and give the answer. Optimal. Predict the behavior of the system. Okay. So, for example, I can measure your weight, your age, your physical activity, and have these information. Then I can actually guess that how much power do you have. Power do you have, okay? So MPC get the information from the grid or from the system, and based on that can actually predict the next stage. So we see what is the logic. This is not the fault prediction. This is more reaction, okay? So if you have the model of the grid, it provides the next stage or can guess the next stage. It is not 100% correct, but somehow it can be correct, okay? In comparison with PI controller, you always follow the reference. So it means that something happening and the PI controller follow it. So if the current is changing like this one, PI controller follow the current. But in MPC, you predict the behavior of the system. So let's see, and then later we can get a better idea. So, and then MPC offers easy tuning compared to other advanced control methods. So this is also one important thing. When we are talking about the other advanced control methods, what is the advanced? Do you believe, for example, PI controller is an advanced control method? No, it's a conventional method. So, but advanced, like based on machine learning, artificial intelligence, this type of things, reinforcement learning and these type of things, I mean, MPC is much more better. MPC is capable of controlling variety of process. For example, power grid control, renewable energy integration due to its ability to handle multivariable system and constraint effectively. So it means that, you know, beside, I mean, it has some possibility to control different parameters, okay? So, for example, you can keep the operation of the converter in a way that, you know, we have the stable voltage when the fault happening. So it means that it limits the current that converter somehow inject to the grid, because when fault happening, current increased. So it limits the current, and by this limitation for the current, we can keep the voltage more stable. And in MPC, the handling of constraints are conceptually straightforward as they are formulated within the optimization problem. So it means that in MPC, you can optimize something by some condition. Okay, optimize the losses and keep that functionality. For example, current between this one and that one. So you have in optimal function, you can consider this type of functionality and optimize the system. MPC is useful when future references are known or can be predicted accurately. So this is based on the dynamic of the system. We see that how it's possible. But there are some also drawbacks for the MPC. The derivation of control law is more complex in MPC than in classic PID. Yeah, because that one is the linear, this is non-linear. So this is a number of the actually system or a variable or more, so it is more complex. In the case of adaptive control, all computation must be carried out at each sampling time. Does anybody know what is the meaning of this? So MPC happening, actually the analysis happening when we have the discrete. So it means that for each step, we need to again make the system actually running and get the answer. So it is a very time consuming, and you need a very high speed processor. An appropriate model of the process must be available for MPC to function effectively. Otherwise, if you ignore something, the system probably provides the wrong answer. Any questions so far? Arya, is it clear? Yeah. So explain that why do we need actually this drawback? What is the meaning of in the case of adaptive control, all computation must be carried out at each sampling time? Mm-hmm. So one process at a time. Mm-hmm. Okay. I didn't get, but probably 50% correct. So it's like in this time we are here, and we calculate something, and then we go to this step. Again, we should calculate again to see answer. Okay? Yeah, this is easy as easy as possible. So we have two types of the actually control scheme: is a indirect MPC and direct MPC. So in indirect MPC, we have actually modulator, which like a PWM. So we use that one, and then provide the signal for the or reference for the converter, and converter will work accordingly. But we have also direct MPC. So for this case, we don't have any PWM. So the switching state function will be created by MPC. Does anybody know how? So, if you listen to me one time, you easily understand it, okay? So this is my converter, okay? This is my converter. So we saw from the simulation that we have a space vector PWM, and it gives the pulse to the gate, and based on that, we inject power to the grid. Okay? So in our simulation, we saw that we are going to compensate the IL. Okay? So we said that our reference is IL, ILD, and ILQ. So I delta I will be equal to IL. D minus ICD delta IQ will be ILQ minus ICQ. Okay? Up to here is clear. Am I right? Oh. And then we run the simulation. The expectation was that this should be equal to 0, and this should be equal to 0 if in the steady state, if the controller is working well. Yeah? So it means that converter inject the same current as load. So for this case, we have the minimum error, or error is equal to 0. It means that what we expect from the converter is equal to what we inject from the converter. So converter is working well. Is it here? Does anybody can say, I don't know this one? Arya? It's clear, yeah? So now the question is that something is clear is that if the reference current and measured current are the same, it means that our controller is working well, okay? So then we calculated the dn alpha and dn beta based on the equation, and then we provide the switching and converter and see that it is working well, very well. Now I remove this part, a space vector PWM. But a space vector PWM is based on the switching state function 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, and we have 1, 1, 1, and also we have 0, 0, 0. So this is the 0 point. We can neglect these two parts. We have 6 operating conditions. Okay? So, assuming that I have a switching state function with this. So I said that my delta I is IL minus IC. I put this one in the converter. The switching is like this one. Switching. So this is the transistor 1, 2, 3, 4, 5, 6. Okay. So this is VA, VB, and VC. Okay, VA, VB, VC, and this is the DC value. VDC. What we have is this one, okay? So when we said that 1, 0, 0 means that this is on, this is off, this is off, this is off, this is on, this is on. 1, 0, 0, 1, 0, 0 means that this is on, this is off, and the lower arm off, on. Okay? Is it clear so far? So, I put this one and measured the value of the current. I see that, okay, this delta I for 1, 0, 0 was equal to 0.2. And then I put this one. For switching 1, 1, 0, delta I is equal to 0.22. And then I put 0, 1, 0. This one. And delta I is equal to 18. And I put again 0, 1, 1. And delta I is 187. And then I put 0, 0, 1. And delta I is 116. And I put last one 101. It is 23 delta I. Okay? So we put 6 operating conditions for the PWM and measure the ID and IQ, and delta I will be this. So what is the optimum operating condition? What is the best answer? So, yeah. So it means that this one is the answer. Okay? So instead of providing switching function based on the order, we optimize the operation of the switching and get the best answer. So this is direct MPC means that we provide the switching state function. If you didn't get it, tell me. Is it clear? You see that, okay, this is the objective function, minimize it, and then that's all, the answer. Udaya, do you have any question? No, thank you. I'm a little bit afraid asking a complicated question and then, oof. Okay, good. So, Arya, was clear? Yes? If I ask you to provide the ion, you cannot, okay? Yeah, why?
I'm just the thing that...
Okay. So you get the routine, that's enough, okay? You just get the why we are going to do it. Otherwise, I mean, later if you want, you can follow with more detail. But the idea is that, you know, how it works. So this is important you understand the concept. So, MPC control, actually, we basically provide the function for that one. We have the different types of the function, but the most popular one is actually defined here. I can show you how it works. But basically, we use the discrete time because we are going to go from this step to this step. In continuous, it's not based on the steps, time steps. But here we have actually different. The formulation is based on the discrete. So you can get the system in continuous time. The dynamic model is that. But we can convert it to discrete time. It's very easy. We will see how. And we have also state vector, which is the variable, key variable we have. It can be like, for example, di to dt, the changes we had in dynamic model. So this is some things that we have. And also we have some input that provide the input for the system, and we consider the operation of the system based on that. So if we are going to actually present that one, it's like a dynamic model of the system, which in this case we have the dx to dt equal to ax plus bu. And if you remember, we calculate the dynamic model of the grid-connected converter based on the di to dt equal to a matrix times to I plus something times to function, switching state function times to something, okay? So here we have actually that matrix A, matrix B, we have the variable and input. So for this case, you need, again, get back the first of the chapter 3, first part we mentioned that if you are going to design a controller, you need to know what is the dynamic model of the system. So when we have the dynamic model of the system, we can go further. So xt is the actually representing the variable that we are going to control. So it can be voltage, current, whatever you want. And also ut is the control input. It can be switching a state function or some other things. And we have A and B, which is the system matrix that we saw how we can calculate it in the chapter 4. Okay? Up to here is clear, yeah? There we mention, okay. We mentioned something like this. This x dot is equal to ax plus b u. Okay? But there, look. We have the dynamic model of the system. And based on that, we can consider the variable and inputs. So This is the control objective. In SPC, the objective function can be divided by this, but we have different other forms. So we can see that, for example, in our control technique, if we are going to provide this model here for the switching, we mentioned the reference value minus measured value power 2. And UCO can be actually any control model. So after that we have constraint. So it is saying that, you know, this is the function, and the system, for example, RU is based on U max and U min, so it can be between 1 to -1, and X also variable can be between something 10 to 25, something like this. So constraint is important. So for example, in grid forming converter, when we are going to define the fault right through capability, we said that, okay, the current should be not more than 20% more than nominal current of the converter. So when the fault happening, if we consider fault right through capability, in fact the converter is working well, and the current will be limited to maximum possibility. Otherwise, if we don't consider this one, the converter will be burned. Then we have the prediction model. So it means that in a dynamic model, we can consider the state for the next one based on the dynamic model of the system. So in a state of here, we said that dx to dt, we consider that x k plus 1, the next step. So here we see that x in time t k plus 1 is equal to ax t plus k and b u t plus k. So I think this is a little bit just a mathematical equation, so probably it's a little